Today we're looking at section 3.1, beginning of chapter 3. We're talking about functions, and we want to remember that a function, and we call that f, is a rule that assigns to each element x, or input value, in a set A exactly one element called f of x in a set B. So the key thing is your x value is your input value, and all those input values together are set A. And then the f of x is the output value, which in the past we've always called that y. But that comes when you look at all the f of x values, that is all those values together are set B. This f parentheses x is read f of x. It is not f times x, so you have to be a little bit careful with that. It's f of x, and what that means is x is your input value, and then you apply the f function to that input value. Another way of reading that is the value of f at x. The domain is the set of the x values from set A. And these, again, like I mentioned, these are the input values. So the domain, input values. These are x values. The range is a set of all possible values of f of x, as x varies through the domain of f, and that just means if you put in any value of x, what are the values of f of x that can come out of that function? The independent variable, this is the symbol that represents an arbitrary number in the domain, and again, typically we use x for that, and x is that independent variable because we get to choose any x value that we want to plug into the function. The dependent variable is a symbol that represents a number in the range. And again, what we've talked about, that's going to be f of x. Two ways we can think about a function. One way we can think about it is that it is a machine that changes each input value in a specific way to produce the output value. So it's this machine that does a certain process every time. Another way we can think about it is as a set of directions that tell you what operations to perform on each input value, on each number that you put in. And either one of those, you're really thinking about the same thing, but you might be able to latch on to a different one of those descriptions depending on how you think. Okay, an arrow diagram or a mapping diagram is a diagram in which each arrow connects an element of A to an element of B. So as you can see here, we look here at negative 2. Negative 2 is getting mapped to the negative 4 over here, and it's also getting mapped, let's try a different color here. So negative 2 is getting mapped to negative 4. It's also getting mapped to positive 1. And then we look at 1, it's getting mapped to negative 2. And then 3 is getting mapped to 2, and 3 is getting mapped to 3. An explicit domain is a domain that is clearly stated. So if I tell you the domain is the numbers 1, 2, 3, and 4, that would be an explicit domain. I'm telling you what the domain is. An implicit domain is a domain that contains the set of all real numbers such that the expression is defined as a real number. What that means is, for instance, we've talked about some limitations with domain. For instance, you can't have a negative inside of a radical, inside of a square root symbol, and so we could limit a domain so that that didn't happen. Because if we put in a negative in there, we're going to get imaginary numbers. Or another possibility is fractions. We have talked about that you can't divide by 0. So a limitation here for an implicit domain would be we are going to use all the values except for the values that make a denominator equal to 0. So we've talked about that in the past, but we haven't talked about the specific term for it. So as we look at example 1, we want to evaluate, or our function is given as f of x equals the absolute value of x, and we want to evaluate f of negative 6. So what this means is that the negative 6 is our input value. So f of negative 6 is going to equal the absolute value of negative 6, and we know that that is 6. oops, I put negative x. This should be negative 6. Sorry. Then when we do the next one, our new input value is 7. So for the next problem, we've got f of 7. And so that means we're going to take the absolute value of that input value, which is 7, and the absolute value of 7 is 7. And then for our third one, notice the input value here is 0. So f of 0 means we're going to take the absolute value of that input value, 0, and we get 0. The absolute value of 0 is 0. Part B, state the implicit domain and the range of the function. Well, if you think about it, are there any limitations on numbers? Is there any number that we cannot take the absolute value of? And the answer is no. So our domain is going to be the set of all real numbers. We can take the absolute value of anything. And again, the limitations on domain come from those two situations we talked about. When you have square roots, you can't have negatives inside of there, and when you have fractions, you can't have a denominator that's equal to 0. So our domain is just all real numbers. When we look at the range, think about the numbers we're getting out of here. When you plug in any number into an absolute value function, the lowest value you can ever get is, and hopefully you're all thinking about it, the lowest value you can ever get is right here, it's 0. So here's how we write this in set notation. Our range is going to be the set of all f of x values, and this line here means such that, I think we've maybe done that before, but such that f of x is greater than or equal to 0, because all the values we get out of this function will be greater than or equal to 0 for the range. Then finally, drawing a mapping diagram for these values. We were given, and I'm just going to draw kind of a circle here. We were given 3 values in the domain, negative 6, 7, and 0. And we're going to map them to the range, and I'm going to go ahead and label this. And our answers were 6, 7, and 0. So negative 6 got sent to 6, 7 got sent to 7, 0 got sent to 0, and that's how difficult a mapping diagram is. It's not very difficult. You just have to write down your values in the domain and then put arrows to what they get sent to in the range. When we evaluate functions, and we just did a very simple example, the x simply acts as a placeholder for the input value. So when you see f of x and then this whatever stuff is after it, that x in the expression is just acting as a placeholder, waiting for you to put in a specific input value. So now we're given f of x equals 5x squared minus 2x minus 3. So when we evaluate f of negative 3, all we're going to do is copy down our function that we're given, 5 times something squared minus 2 times something minus 3. Notice I just replaced each of these x's in the function with parentheses because that's where our input value goes. Well, the input value is right here, negative 3, and that's what goes into each of those spots. So now we've got 5 times negative 3 squared, which is 9. Negative 2 times negative 3 is plus 6 minus 3. This gives us 45 plus 6 minus 3, and that's going to be 48 for part A. Part B, same thing. 5 times our input value squared minus 2 times our input value minus 3. And this time our input value is 0. So we just plug in a 0 and a 0. So this gives us, and hopefully we know this, 5 times 0 squared is 0. 2 times 0 is 0 minus 3. So our answer is negative 3. Over here when we look at f of 2, again, same concept. 5 times our input value squared minus 2 times our input value minus 3. And this time we're plugging in the input value they give us is 2. So this is 5 times 4 minus 4 minus 3. So 20 minus 4 minus 3 equals 13. And then the last one, We've got a decimal here, but again, works the same way. 5 times our input value squared minus 2 times our input value minus 3. This time we put in 0.5 because that's our input value. So 0.5 squared is 0.25 times 5 is 1.25. 0.5 times 2 is 1, and then minus 3. And so we get negative 2.75. So again, the x value is just a placeholder. You can put parentheses there, and then you know that's where I'm going to put in the input value that I'm given for a specific function. Let's take a look at example 3. It's a word problem. It says a cell phone company charges $39.99 for 450 minutes of calling. Then it charges 45 cents for each additional minute. Describe the situation with a function, and then find the charge for 100 minutes, 400 minutes, and 480 minutes. As we look at this, this has to be a piecewise function. So let's write f of x, and let's see if we can describe this. Hopefully it seems pretty simple that the function is going to equal, or the cost is going to equal $39.99 when anytime you use an x value that is less than or equal to 450 minutes. Does that make sense? Hopefully, that they're charging $39.99 for the first 450 minutes. Now this is where it gets a little bit tricky, because for the second part, when we have x greater than 450, that's the second time that we have to look at, second situation. What are they charging? They're charging their base fee of $39.99, but then they're adding 45 cents for each additional minute, and that's the part that's a little bit tricky. The 45 cents isn't tough, we put 0.45, but how do we figure out each additional minute? Well, the number of minutes used is the x, but to make it each additional minute, we have to actually subtract 450 because we've already paid for those first 450 minutes. So that would be an example of how we can come up with that equation. So now it says we want to find the charge for 100 minutes. So what is f of 100? Well, you guys have all looked at this before. So 100 minutes, it's less than your total number of minutes that you get, so that charge is just the flat $39.99 because it's under 450 minutes. It's in this part of the function. Then we have a charge for 400 minutes. Again, that 400 is less than 450, so the charge is just $39.99. That's already taken care of in your monthly fee. Then we have the charge for 480 minutes. So f of 480. Well, now we have to go down to, we're in this area, right? We're more than 450, so we use the second formula. So we have $39.99 plus 0.45 times 480 minus 450, and so that is $39.99 plus 0.45 times 30, and that gives us $13.50 when we multiply that together. And so $39.99 plus $13.50 gives us $53.49. So that would be our charge for 480 minutes. So you can see it's definitely, if that was your price range, it would be definitely a good idea to stay under that because the minutes start costing a lot very quickly. And here's another example of evaluating functions, only this time we're given some variables as our input value, but we do the same thing, f of a. Well, 4 times our input value squared minus 2 times the input value minus 3, and we plug in an a and an a. And so this one, there's not even really any simplifying. We have 4a squared minus 2a minus 3, and that is our answer. So again, the x in the function just acts as a placeholder for the input value. We do the same thing for b. 4 times the input value squared minus 2 times the input value minus 3. And this time we're putting in negative a. So negative a, negative a. So this gives us 4 times negative a times negative a is simply a squared. Negative times a negative is a positive. And then negative 2 times negative a is positive 2a and minus 3. So that's our answer for part B. Part C gets a little bit longer because our input value is longer. So we have 4 times the input value squared minus 2 times the input value minus 3. But this time we're plugging in a plus h to both of these spots. So we've got 4, but we have to FOIL this out now. A plus h times a plus h. I'll do that in a second, but then this one, it just distributes, so we get negative 2a minus 2h, and then we have minus 3. So we still have 4 times, and this is a squared plus ah plus ah again plus h squared. The rest of this doesn't change. And then we just distribute. Let's think about this. This is 2 times ah. We've got 2 of them there. So now let's distribute. You get 4a squared plus 8ah plus 4h squared minus 2a minus 2h minus 3. And that gives us our answer for that one. So that one takes a little bit longer, just because you have to square that binomial, and that takes a little bit more time to do. The last part of this example is what we call a difference quotient. And so it's the same function, but notice it's a combination of a couple functions together. Now, as you think about it, we really, the two things we need to know before we start are f of a plus h and f of a. Okay? We actually just did both of those, didn't we? If we think back, f of a plus h was equal to 4a squared minus 8ah plus 4, I'm sorry, that should be a plus 8ah, plus 4h squared minus 2a minus 2h, and what do we have at the end? Minus 3. And f of a from the previous slide was 4a squared minus 2a minus 3. So we've already figured out those two pieces. So what we're going to do is simply plug those in. So the first one is 4a squared plus 8ah plus 4h squared minus 2a minus 2h minus 3. And then minus, that's right here. Now we're going to subtract f of a, which again, we've got that right here. So we're going to subtract 4a squared minus 2a minus 3. And that is all divided by h. So now the key thing is here, we just need to distribute the negative through to each of these. So I'm just going to rewrite the first stuff. 4a squared plus 8ah plus 4h squared minus 2a minus 2h minus 3. And now it's minus 4a squared plus 2a plus 3. And that's all divided by h. So now, what happens in these is, you'll see right now, notice the 4a squared can cancel with the negative 4a squared. Then the negative 2a can cancel with the positive 2a. And the negative 3 can cancel with the positive 3. So what we have left is this, 8ah plus 4h squared minus 2h divided by h. Now again, think back to when we divide. Notice each of those things have a factor in them of h here here, and here. So we can factor that h out. So this is now equal to h times 8a plus 4h minus 2, and that's still over h. And so now this h can cancel with this h. And our final answer is just 8a plus 4h minus 2. And actually, anytime you see a difference quotient like that with these functions that are polynomials, that's going to happen. You're going to have a bunch of stuff cancel out, and then the h's will cancel out, and you'll be left with something that looks like that. All right, identify the implicit domain for the following functions. This is where we have to check out those limitations, fractions, and radicals. So notice the first thing here in part A, we want to factor the denominator because we can't let this denominator equal 0. So when we factor this, we have an x and an x. Again, the signs are the same and both negative, so minus and minus. And factors here that will work for 2 are 2 and 1. So we have to make sure that this thing does not equal 0, so that means x minus 2 cannot equal 0, and also x minus 1 cannot equal 0. So that means x cannot be 2. It also means x cannot be 1 when you solve each of those. So the way we write that is we can use any x such that x does not equal 2 and x does not equal 1, and then we write it with our set notation, the braces. All right, the next one, g of x. Oh, here we have a radical. So here's the deal with the radical. We know that 4 minus x squared has to be greater than or equal to 0. Now the tricky part here is that this is 4 minus x squared. It's a squared term. It's not just get the x by itself. So here's what happens. We can get the x by itself by adding x squared to both sides. And then we take the square root of both sides like we normally would. But here's where things get messed up. We get plus or minus 2, but we have this inequality symbol. So what we have to think about here is we've got this range of numbers on the number line, and you've got negative 2 and you've got positive 2. We know those values are included in our solution, but then we have to figure out, is it the inside part that is okay, or is it the outside parts that works? So what we'll do is we'll just check a value. So let's say I check 0, and I plug that into here. 4 minus 0 squared is greater than or equal to 0. Yes, that is true, so that means anything in this middle section will work. If I plug in, let's say, a 3, and I check that out, 4 minus 3 squared is greater than or equal to 0. Well, 4 minus 9 is not greater than or equal to 0, so that doesn't work. And you can see the same thing would happen over here with negative 3 if you plug that in, because negative 3 squared will also be 9. So the area that works is this middle part. So our domain for this one, we can use any x such that negative 2 is less than or equal to x is less than or equal to positive 2. We've got to have that interval for this function to be okay. And now here we're dealing with a t. Notice we've got a fraction and a radical. So for the fraction, first of all, we know that the square root of t minus 2 cannot be equal to 0, which means t minus 2 cannot be equal to 0, and so t cannot be equal to 2. So that takes care of the fraction. But we've also got the radical. So we know that the stuff inside the radical, t minus 2, cannot be negative. It has to be greater than or equal to 0, but again, we've already stated it can't be equal to 0, so we're just going to say greater than 0. And we add 2, and we get t is greater than 2. So t can't be equal to 2, t is greater than 2. It's all taken care of in this statement right here. So our domain is t's, any t such that t is greater than 2, and we put our braces around it. Notice I don't have to repeat that because this one already says t can't be equal to 2. So I don't have to repeat it. More methods to represent a function. We can talk about it verbally with words. We didn't do much of that. Algebraically, using a formula, we did that. You can represent functions with a graph visually, and then numerically using a table. We showed that kind of with the mapping diagram. But it's all basically trying to relate the x value from the domain to the y value, or the f of x value from the range. The problems to take a look at here for section 3.1 are there on those pages, and so again, you'll have time to work on that in class tomorrow. So take a look at some of those, and so that you're ready to ask any questions that you may have.